Hello everyone, my name is Yu Sasaki from NTT Secure Platform Laboratories. So I'm going to present our paper accepted by ACNS2020, which is entitled Lesamnta-Lightweight Revisited, Improved Security Analysis of Primitive and New PRF Mode. And this is a joint work with Shoichi Hirose from University of Fukui and Hirotaka Yoshida from National Institute of Advanced Industrial Science and Technology. Here I give the research overview. Our target is Lesamnta-Lightweight. Lesamnta-Lightweight is a lightweight cryptographic hash function standardized by ISO/IEC. Lesamnta-Lightweight is the only one optimized for software implementations in this category. The designers provided primitive security analysis against differential cryptanalysis by using Viterbi algorithm. The design of Lesamnta-Lightweight was extended to support pseudo-random function modes. In this research, we have two kinds of contributions. One is for the primitive and the other is for the mode. For the primitive, we use mixed integer linear programming to evaluate the primitive. We show that Lesamnta-Lightweight is more secure than originally expected. One may reduce the number of rounds by 25%. This achieves 25% speedup. For the mode, we propose a new PRF mode achieving double throughput compared to previous modes, and we prove its security. This slide shows recent trend in the design of lightweight cryptography. In early days, each primitive is designed to support each function. So one scheme for encryption, and one design for hash function, and another design for authentication. But nowadays, a single primitive supports many functionalities via the mode. Indeed, NIST is organizing a design competition to standardize lightweight cryptographic schemes. And in this competition, supporting both authenticated encryption and hash modes is regarded as an advantage. Moreover, if the scheme supports hash mode, it must resist the attack for the MAC usage, which is called length extension attack. Here, I revisit the design progress of Lesamnta and its related designs. Originally, Lesamnta was designed for the SHA-3 competition. During the competition, a third party pointed out a security issue due to the sparse constant of Lesamnta. Then, the design was patched, and no flaw has been detected after that. The design of Lesamnta was optimized to be lightweight, and this design is called Lesamnta-Lightweight. Lesamnta-Lightweight was internationally standardized by ISO/IEC. Finally, Lesamnta-Lightweight was extended to support PRF. There are three methods to support PRF. The first one is to use the key prefix method. The second one is to use key via IV plus truncation framework. And the last one is to use key via IV and Markov-Dangar permutation framework. This page shows the design of Lesamnta Lightweight in the mode level. Lesamnta Lightweight adapts a block cipher-based mode. The underlying block cipher, which is called Lesamnta Lightweight block cipher, supports 256-bit block and 128-bit key. Security of Lesamnta Lightweight is based on the ideal behavior of Lesamnta Lightweight block cipher. So the diagram of the computation is illustrated at the bottom. In each block, 128 bits of the message is injected as the half of the plaintext. And the results of the block cipher computation is fed to the next block. The structure of Lesamnta Lightweight BC is explained in this page. A 256-bit plaintext input to Lesamnta Lightweight BC is divided into 4 64-bit branches. It performs 4-branch type 1 generalized phase-tail network for 64 rounds. And one round of the computation is illustrated in the left-hand side. So in this figure, each cell corresponds to 1 byte. So each branch consists of 2 columns. And the G function is applied to the third column. G function is based on AES. Because the number of columns for the branch is 2, shift rows operation is replaced with a byte shuffle operation. So in the G function, the key is XORed to the left column, and then the sub-bytes is applied to each cell, and then the mixed columns is applied for 2 branches, and the byte position is shuffled. From here, I introduce our results. The first part is about primitive, and we update security analysis of Lesamnta Lightweight BC against differential cryptanalysis. This page is about previous security analysis. The designers evaluated the security of Lesamnta Lightweight block cipher against differential cryptanalysis. The maximum differential probability of AES box is 2 to the minus 6, and the Lesamnta Lightweight offers security against 2 to the 128 attack attempts. Then, it is important to ensure at least 22 active S boxes. The maximum differential probability becomes 2 to the minus 132. The designers counted the number of active S boxes by using Viterbi algorithm. It was proven that the number of active S boxes is lower bounded by 24 for 24 rounds. Thus, the full specification that consists of 64 rounds is secure. Note that this is a lower bound, so the tightness was unclear, and the security beyond 24 rounds was also unclear. In this research, we applied 2 previous works to evaluate the security of Lesamnta Lightweight block cipher against the differential cryptanalysis. The first one was done by Moha et al. And presented at INSCRIPT 2011. And they converted a problem of finding an optimal differential trail into an optimization problem for mixed integer linear programming. Then, Chang et al. At ISC 2018 showed how to speed up differential trail search with MLP. By combining those 2 works, we could evaluate the number of active S boxes of Lesamnta lightweight block cipher very efficiently. A challenge to apply MILP is to model all possible differential propagations with a set of linear inequalities. We carefully described the model for Lesamnta lightweight block cipher in the paper. In this talk, we omit the details. The evaluation results are shown in the table. As mentioned before, ensuring 22 active S-boxes is important for achieving 128-bit security. We found that 18 rounds are sufficient to ensure more than 22 active S-boxes, while the designers needed 24 rounds. From this ratio, one may reduce the number of rounds by 25% by preserving the same level of security as the designers originally expected. Given that the block size of Lesamnta lightweight BC is 256 bits, to ensure 43 active S-boxes is important. We found that even in this high security level, 30 rounds, which is less than a half of the full specification, is sufficient. MILP returns a tight bound. So, if a bound is provided, then there should exist differential trail that matches the bound. For 24 rounds, the previous lower bound of 24 was updated to the tight bound of 33. And here, as an example, we show the differential trail that matches the bound. Namely, the differential trail having exactly 33 active S-boxes. Other than the number of active S-boxes, we studied several aspects of Lesamnta lightweight BC. The first one is to investigate if there exists other choices of the shuffle operation to have a better security. We found that the choice of Lesamnta lightweight BC is the best. We also evaluated the related key differential cryptanalysis. We showed that it is impossible to obtain meaningful bounds only by counting the number of active S-boxes. Those studies are detailed in the paper and we omit them in this talk. From here, I present the second part of our results, which is the new PRF mode. This slide compares hash function and PRF. The interface of hash functions and PRF are similar. Both take an arbitrary length message as input and generate a fixed length random looking output. PRF is a keyed primitive. It is known that the finalization computation needs to be analyzed carefully to prevent length extension attacks. This slide shows 3 previous PRF modes supporting PRF. The first one is called key prefix. The best thing this scheme is the specification of Lesamnta lightweight is not modified at all. It just prepends 120-bit key K before the message. The good thing is the key size is 128 bits. However, the security is ensured by truncating the last output. So the size of the generated randomness is only up to 128 bits. And it needs to compute additional block cipher code E to process the key input. The second scheme replaces the IV of the Lesamnta lightweight with key K0 and K1. So it requires to use 256-bit key. And the security is ensured by truncating the output, so the size of the generated randomness is up to 128 bits. The best thing in this scheme is no additional computation is required compared to the original Lesamnta-LW. The last scheme is called MDP, and the IV is replaced with a key, so the key size is 256 bits. But the best thing for this construction is that the last output does not have to be truncated. So the size of the generated randomness is up to 256 bits. The construction must compute some public permutation pi before the last block. But this pi does not have to be strong. So the computational cost is much cheaper compared to computing additional block cipher call in scheme 1. The previous 3 modes process only 128-bit message input per block. If the block size is 256 bits, we may want to process 256-bit message input per block cipher call. And combining several features explained in the previous page, our goal is to make the key size to be 128 bits and to have output size of 256 bits. Well, the overhead should be ideally 0, but additional computation of pi might be accepted. And the main goal is to increase the number of processed bits per block to 256 bits. We found that there were 3 possible ways to increase the number of processed bits per block. For all of the 3 methods, we only process 128-bit key in the first block. The security can be ensured either by truncation or MDP. And for MDP, we further have 2 choices for the position that the pi is applied. If the truncation is adopted, then the output size is only up to 128 bits. So ideally, we want to choose one of the bottom 2. As a result of our analysis, we found that truncation and MDP for the state are insecure, in that the tags only with 264 attempts are demonstrated in the paper. In the end, MDP for the key is the only choice that is provably secure. We proved its security when pi is efficiently instantiated with a constant XOR. And the security proofs in the standard model and the ideal cipher model are available in the paper. I conclude this talk. In this research, we revisited the design and the security analysis of Lesamnta-LW, which is an ISO IEC standard for lightweight cryptography. For the primitive, we evaluated the number of active S-boxes with MLP. It turned out that Lesamnta-LW is more secure than originally expected. It may be possible to reduce the number of rounds by 25%. For the modes, we propose a new PRF mode based on Lesamnta-LW BC that achieves the double throughput. And we proved the security of our construction. Thank you for your attention.